Okay, so welcome to video 3 in this course, ST3, where this part of the course we're talking about discrete variables, such as coin tossing or rolling the dice. So if we roll 2 dice, it's quite predictable that we have options between values of 2 and 12, and therefore we can look at the combinations that give us these different options. That getting 2 means we rolled 1 and 1, whereas getting 12 means that we roll 6 and 6. Whereas for rolling 7, we have different options, like 4 and 3, or 3 and 4, and so on, 6 and 2, 2 and 6, 1 and 6, 6 and 1, which means they have more chances of rolling this particular outcome. So talking to do when we think about biological data is we may have different categories that are present, as shown across here, but the distribution may not have that sort of symmetry. So if we plot the distribution and the frequency, it may be a bit all over the place. So what we can think about is plotting some sort of expected value referring to the expected value of x, any value in our distribution, given their set of all different values. So it's like an average value, but it's not the exact same. It's a kind of weighted middle value. So what we do here is calculate the sum of all the values that are present. So this might be category 1, 2, and 3, and so on, and multiply by the frequency that we see across on our y-axis here. That's the frequency. So we might be dealing with a distribution that looks like this. And we have the weight of 1 for x1, category 1, same for weight 2 for category 2, same for category 3 and 4, and so on, and you sum these up. So if we have, for example, expression rate and RPKM of 20 different genes, we might have the frequency of the different expression rates for the different samples distributed right here. You might find that 5 is high and 6 is high, the other ones are a bit low. So what we can do is multiply the value 2 by their weighted by their frequency 3. So this is going to list the data that we can expect. So we can adjust that for the number of values that we have, so 3 divided by 20, and multiply it by our expected values. So we get 2 by 3, and they're all going to be over 20 ultimately, plus 3 by 5, plus 4 by 3, plus 5 by 6, plus 6 by 2, plus 7 by 1. So that's going to give us 21, 33, 63, 75, 82. So expected value is going to be around 4.1 there. So that kind of gives us some sort of sense of what our value will be. So it's going to be lying around here. If we calculate that here, we can see it more explicitly, that we get 4.1 for this. And this gives us an example that we can think of when we're doing coin toss examples that we're going to go through now. But really, it's the same thing. We're just looking at heads and tails instead of heads, tails, and other different options. So in this case, we're looking at binomial probabilities. We have P and Q, and they sum to 1. This means P is equal to Q minus 1. Q is equal to P, 1 minus P, and P is 1 minus Q. So all be left over. If we're multinomial, we can just expand those different options. So we have P plus Q to the n, the number of multinomial categories that are present, and that gives us this expansion. So this expansion may look challenging. What we can think about is the number of options that are present, like n equals 1, n equals 2, n equals 3, and how we can fit different categories into these. So this is the expansion for n equals 1. It's simply P plus Q to the power of 1. This is P plus Q to the power of 2, P plus Q to the power of 3. And if we expand these out, we can think about having P plus Q, then P squared plus 2PQ plus Q squared plus having, and then for the next one is going to be P cubed. Sorry, my pen is slow sometimes. 3 by P squared Q plus 3Q squared P plus Q cubed, and so on. So you sort of see a pattern there. So we have this will be obviously P to the power of 4, and guess the next value is going to be 4 by P to the power of 3 by Q, and so on, all the way down to Q to the power of 4 at the end. So there's a particular pattern here, and that's known as Pascal's triangle. So this, we see the first pattern here is 1 and 1, which corresponds to P plus Q, p squared plus 2pq plus q squared to the pattern 1, 2, 1. And we can continue that then 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 15, 10, 5, 1, and so on. And you see that as a triangle here. So essentially how we have the zero values here, and we just add them up. So 0 plus 1 is 1, 0 plus 1 is 1. Here, 1 plus 1 is 2, 1 plus 0 is 1, all the way down here. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 10 is 15, and so on. So it's actually quite a predictable series that we can use Pascal's triangle to quickly work out what they are. And this can be denoted as an expansion that we can use then for our probability options. So we can ask then, if we have n events, what's the probability of k occurrences of that? So for coin toss, we have probability p is equal to half, which is equal to q for convenience. And therefore we can ask, if I toss a coin 3 times, what's the chances of getting 1 heads? So the only option that doesn't have that is tails, 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 and therefore we know the probability of getting that is going to be half by half by half, which is 1/8. So therefore the probability of getting this is going to be 7/8. But let's work it out using a formula that we can generalize to all these different options. So if we have here, we're looking at the probability of 1 given the probability of a half. We've got n equals 3 and k equals 1. We've got a half to the power of k by half to the power of n minus k. It's squared, and that's 1. We're going to get 3 factorial over 2 factorial, which is just 3 by a half by a half by a half. So when we work this out, we'll be able to work out what's the chance of getting one head, exactly 1 head in this case. So the other one was 1, 2, or 3 heads. Here it's exactly 1 head, which is going to be 3 divided by 8. And that's going to be symmetrical. So we can plot the probability of getting 1 head is 1/8. 0 heads is 1/8. 1, 2, and 3. So but this is 3/8 for 2 heads, and then 1/8 for 3 at the end. And this is our frequency on this axis. And that corresponds to 3 out of 8. And this one is 1 out of 8. So this can be generalized that we can ask then, so what's the probability of getting particular value of heads out of a particular number of events. That can be generalized to, say, coins. So maybe you have 6 different categories of coins. We're asking what's the probability of getting, given we're looking at rolling 3, given the probability opposite we have, which is 1/6. What's the probability of getting a particular pattern of options that are present? These are all 1/6, and there's the power of the values of k that we for our set of observations. So multinomials are just an expansion of binomial probability. So you can see here when you visually look through this option of getting, say, 2 heads, that we can describe it in the same way. We've got 3 factorial, and we're going to for n factorial, n k equals 2. This is n minus k here by half to the power of k by half to the power of n minus k, which is equal to 2. And if we look at the options graphically as well, we're asking, I probably have any 2 heads. If we look at the different options, we've got head, head here, head, head here, head, head here, which corresponds to 3 out of the 8 options. So we can check properly if this is correct by watching out the events. And therefore, we can think about things. So say we are running a trial and we have 300 different samples, but the chance of infection is 0.2. What's the probability of observing k exactly 80 as being infected? We can write this as beta 80 given 0.2. And then we can describe that using this formula that we have 300 samples. We've got 300 factorial by 8 divided by 80 factorial, 220 factorial, and probability of infection is 0.2. So it's 1 in 5 to the power of 80 by 4. 4 in 5 to the power of 220. So we can work out that probability, which is going to be low because it's probability of exactly K equals 80 being infected. In R, we could write this as using the choose function, choose 80 by 0.2 to the power of 80 by 0.8 to the power of 220. If we did this, we'd get the answer of about 0.11%. So therefore, we can move on to other questions that link to binomial probability problems. So for example, to continue this, our chance of infection is 1/8 per exposure, and animal is exposed 7 times. What's the chance of becoming infected on the 2nd, 4th, and 6th time, but not on the other exposures? So if you think of these as the days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and it's exposed 7 times. So each time it's 1/5, 1/5, 1/5, 1/5 is the chance of becoming infected on each day because it's independent, assuming for the purposes of this question at least. What's the chance of becoming infected on the 2nd, 4th, and 6th times, but not on the other days? This is an imaginary animal that recovers within a day, but not on the other days. So this is going to be 4 out of 8 for this option, 4 out of 8 for this option, 4 out of 8 for this option, and 4 out of 8. Sorry, 4 out of 5 for this option. So if we multiply all of these together, we can work out what our probability of is going to be. So we just need to multiply this out to get our answer there. If we look at a related question, the chance of infection is 1/5, 1 in 5, 1/5. If they expose about 7 times, what's the chance of becoming infected 4 times? So here we've got our binomial probability problem. We've got 7 choose 4 by 1/5 to the power of 4 by 4/5 to the power of 3. So you got 7 by 5, 7 by 6 by 5, as a numerator by 1/5 to the power of 4 by 4/5 to the power of 3. So if we work this out, as shown here, we get a value of 1.6% with that exact value. If we ask about if the similar one, what's the chance of becoming infected 1 time only? It's the same thing. We've got 7 factorial by 1/5 to the power of 1 and 4/5 to the power of n minus k, which is 6. And again, if we work this out, becoming 1 time only, we can work out in a multiple different ways, and this is one of them. A more complex question: an animal's the chances 1/5 again, where we're exposing the animal n times this time. What's the minimum n such that the chance of the animal becoming infected is 99%? So here we have n choose x events by 1/5 to the power of x by 4/5 to the power of n minus x. So we're asking what's the minimum n such that the chance of the animal infected is greater than 66%. So for example, if we had 10 as our value, we can then work out what's the probability of becoming infected once we have this value, what's the chance of becoming infected with 10 different events becoming infected at least once. So that would be 10 choose 1 by 1/5 by 4/5 to the power of 9 in that instance. So what we're thinking about is actually summing across all the different values from 0 up to n, so that this value exceeds 99%. So if you think about this, the probability of being never infected is 4/5 to the power of n. So becoming infected at least once is therefore going to be 1 minus this value. So saying what's the value for which that is greater than or equal to 0.99. So if we think about this, we can simplify and say 4 to the power of 5 to the power of n is therefore has to be greater than or equal to 0.01. If we solve this for n, we'll be able to get a value of n must be at least 21 when you round it up. Another example is for cattle becoming inoculated with some inoculum of F and DP. 30% chance of becoming infected. If 6 are inoculated, what's the chance of 4 out of 6 will be infected? So that's 6, choose 4 by 0.3 to the power of 4 by 0.7 to the power of 6. So if we work this out, this will work out as about 0.06. In R, you can write this as choose 6, 4 by 0.3 to the power of 4 and 0.7 to the power of 2. Similarly, precedence none will be infected. So here we had 6, choose 0 by 1, because that 1/5 to the power of 0, 0.3 to the power of 0 is 1, and then 0.7 to the power of 6. So if we work this out, this is about 0.12. What's the chance? 5 out of 15 would be infected. So here we got 15, choose 5 by 0.3 to the power of 5 by 0.7 to the power of 10. If we work this out, we'll get a value about 0.21. So if we wrote this in R again, it would be 15 choose 2 by 0.3 to the power of 5 by 0.7 to the power of 10. So this kind of video introduces different aspects of probability ideas on discrete variables, and please see the demonstration videos for more illustrations about how we can write R code to look at this.